this is problem number 17 of part 2, the comprehensive part of the practice final. And this is another true-false question, so we have to evaluate whether the statement itself is true. And the statement is, the presence of solute molecules lowers the vapor pressure of the solvent. And this is indeed a true statement, so, but we need to understand why. And this, the answer lies in two things. One is essentially back to the familiar Boltzmann distribution. This is the number of particles, molecules, whatever. And this is the energy. Well, this would be the kinetic energy. And now, if I have some sort of a threshold here, so E sub A or whatever, Boltzmann factor, it describes where E to the minus E sub A over RT is defined as the fraction with kinetic energy greater than or equal to this threshold energy. Now, the reason this is relevant for vapor pressure is because of the Clausius-Clapeyron equation, where P vapor is equal to some sort of pre-exponential term, which is characteristic of the solution, times a Boltzmann factor. So this is recognized easily as this is a Boltzmann factor. This represents the fraction of the molecules with a kinetic energy greater than or equal to that of the enthalpy of vaporization, which is the energy needed that the molecules need to escape the body, the attractive forces that are holding it in the liquid. And so this is a very straightforward, this is just a fraction, this is some sort of a characteristic number. And so the vapor pressure is going to be proportional to the fraction of the molecules with that much kinetic energy. Well, now how does this get modified by solute molecules? First, you have to take into consideration that in order to escape the body of the liquid, the molecules have to be on the surface. So it's only the surface molecules that are going to have the ability to escape and go into the vapor phase. And now, when you have a solute, some sort of molecule, it doesn't matter what it is. It only matters how many there are. This is going to be a colligative property. It's going to give rise to what we call boiling point elevation. And that arises because the solute molecules are distributed equally, uniformly throughout the body of the liquid, and therefore distributed about the surface as well. And their presence of solute molecules on the surface lowers the number of solvent molecules on the surface. So that means I'm going to have another fraction. This fraction is going to represent the ones with that much kinetic energy, but then it has to be multiplied by another fraction, which is going to reduce the vapor pressure, because only the fraction of the molecules on the surface that are indeed solvent molecules are going to be the ones that are going to obey this, are going to be represented by this corresponding expression for the vapor pressure, the Clausius-Clapeyron equation. And so this gets multiplied by a fraction. And so then the amount of, and we can set this in here as delta H vaporization. And so now, in order to achieve the same vapor pressure, I'm going to have an elevated temperature in order to get the same vapor pressure. So that what happens is there's boiling point elevation. In order for the vapor pressure to be equal to the external pressure and there to be boiling, I'm going to have a higher temperature because I've lowered the fraction of the molecules on the surface that are solvent molecules. So that is why this is indeed a very true statement. So the answer is, you fill in the bubble corresponding to true, which is A, and right may be true on the test. So you have a hard copy to back what you're doing in case there's a problem with your Scantron.